Okay, we're going to now talk about the next type of potential energy, which is going to be elastic potential energy. Okay, so the difference of elastic potential energy for a spring force is equal to, again, minus the work from A to B, equal to 1/2 times the spring constant, K. It's a spring constant, times x sub b squared minus x sub a squared, where x is equal to the displacement. Okay. So we can now write this in a function form as u of x is equal to 1/2 kx squared. Okay, so we're going to go ahead and use this in the next problem. It states a system contains a perfectly elastic spring with an unstretched length of 20 centimeters and a spring constant of 4 newtons per centimeter. Okay, the first part states or asks how much elastic potential energy does the spring contribute when its length is 23 centimeters. Okay, so u, it's going to be u of x, where x is again displacement. Okay, so we have u at 20, or actually x is equal to, I'm just going to write this down, 1/2 kx squared. And x is the displacement. So the displacement that the spring has undergone is going to be the final position, 23 centimeters, minus our initial position, which was 20 centimeters. So our displacement overall is 3 centimeters. Okay, so our u at 3 centimeters is equal to 1/2 times k, our spring constant, so 4 Newton per centimeters, times 3 centimeters squared. Okay, so we'll put that in our calculators. And we get 18, and this is going to be in newtons times centimeters. Okay, or if we want it to be in the proper units, we can go ahead and say for 100 centimeters there's 1 meter. So this would also be 0.18 joules. Okay, now for part B, it asks how much more potential energy does it contribute if its length increases to 26 centimeters. Okay, so it says how much more potential energy. So note that our x now is going to be 26 centimeters minus, since we're just looking for how much more potential energy than this first problem, we can state that our displacement is now 26 minus 23 centimeters with a difference of 3 centimeters. So if we do the math again, it's going to be the exact same. It should be 0.18 joules more. Let me double check that. So it's always good to double check your work. Let me go ahead and actually go through the process. So if this was 26 centimeters minus our true initial, which was 20 centimeters, our displacement would be 6 centimeters. Okay. And so our u of 6 centimeters would be equal to 1/2 times 4 times 6 squared. So that would give us 72. And again, that's in newtons centimeters. So if we apply this conversion, we'd have 0.72 joules. So basically, this first portion I said is not correct. Okay, so our potential energy at 6 centimeters is 0.72 joules. Okay, and so we want to know how much more that is than our first calculation. So let's go ahead and say then our delta, I'm going to say delta U from 6 to 3 is going to be 0.72 joules minus 0.18 joules. And that's going to give me 0.54 joules. So this is my difference in potential energy from these two different points. Okay, so this second one produces this much more potential energy, okay, in the spring. All right, so let's go ahead and move on to another example. This is example 8.4. It states that a block weighing 1.2 newtons is hung from a spring with a spring constant of 6 newtons per meters, as shown in this image. Okay, what is the maximum expansion of the spring as seen at point C? Okay, so the first thing we need to do is kind of set up our problem. So we should have a change, we should have the initial energy, I'll say, equal to our final energy. Okay, so the point A, we should have some kind of kinetic energy and a potential energy. Okay, and at point C, we should have some kinetic energy and a potential energy. Okay, so we need to, remember that kinetic energy is equal to 1/2 mv squared. Okay. Potential energy here, we're going to have two different kinds. We're going to say gravitational is going to be mgh, or mgy. I should put y, because that's how it has in your book. And then our spring is going to be 1/2 kx squared. Okay, so on this first side, we should have some kinetic energy, 1/2 mv squared. At this point, there is no motion. Okay, so v equals 0. So our kinetic energy at A is going to go to 0. Our potential energy, let's look at our gravitational. We state that y equals 0 at this point. So our gravitational is going to be 0. And our displacement for our spring is also 0. So there has been no displacement yet. So again, this will be 0. Okay, so now for this equation, we have 0 equals. Let's look at our kinetic energy at the end here at point C. This is also going to be 0 since it's not in motion. So that will be 0. Our potential energy, let's look at G. This does have some height, okay, but we don't know what it is. So we're going to go ahead and put mg times y at c, okay, plus, let's see if we have our spring, which we do because we have some sort of expansion on the spring, right? So we have some displacement. So we should have plus 1/2 times k y sub c squared, okay? All right, so now we can go ahead and solve this. So we'll have 0 equals mg plus 1/2 k y sub c. I'm pulling out a y sub c here. So this tells us that either y sub c equals 0 or this term is equal to 0. So if y sub c equals 0, that doesn't make sense. We'd be back here. Okay, so we need this equation here. And we want to solve for that expansion, y sub c. So y sub c here should equal, let me pull that over, minus 2 mg over k. Okay. And I will need to start a new page, so, oh, there we go. All right, so we have y sub c is equal to negative 2 mg over k. So we can plug that in. We get 2 minus 2 times, so mg we don't know, but we do know that the weight of the block is 1.2 newtons. And our force is equal to mg here, since it's just the weight of the block. So I will go ahead and put 1.2 here, newtons. And our spring constant is 6.0 Newton per meter. So we can plug that into our calculator. 2 times 1.2 divided by 6, and we get negative 0.4 meters. So this is our maximum expansion of the spring, which is at this point C. Okay? All right. So part B states, what is the potential energy at point B, halfway between A and C? Okay. So we can say that at our halfway point, our distance here, y sub c, or not y sub c, but y sub b, is going to be half of y sub c. So y sub b is going to be 1/2 y sub c, since at halfway point. Okay. So now what we'll have is u sub b, since we're looking at the potential energy, we need to take into account our gravitational potential energy, mgy, again sub b, and our elastic potential energy, so 1/2 k y sub b squared. Okay. All right, so we can just go ahead and plug these numbers in. mg is 1.2 newtons times half of this would be negative 0.2 meters. Oh, I will need to continue in the next video.